Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at the derivative of the logarithmic function. If we were to take a look at the function y equals the log of u base b, where u is a function of x, and we want to differentiate that with respect to x, the derivative will be equal to 1 over u times the log of e base b times du dx. We talked about e in a previous video on logarithms and natural logarithms. E is a special number like pi. It's an irrational number and it goes on and on and on, but it's approximately equal to 2.71828. But like I say, it goes on and on and on. It's a very important number and it can be shown to be tied to a lot of naturally occurring events, and therefore it's a perfect number to use for a base of logarithms and exponential functions. So E is something that you're going to encounter when you look at real life applications of logarithms and exponential functions. If we wanted to do an example of a logarithmic function with any base, so if I had y equals the log of 4x, and when I don't put a base there, it's understood to be base 10. So we would plug into this formula, the derivative of this would be 1 over u, so 1 over 4x, times the log of e, base 10, which we don't need to write our base 10, times the derivative of u, 4x, which is 4. So this would simplify, the 4's would cancel to be 1 over x times the log of e base 10. Now that represents a number, but often you will be expected to keep it in exact form, so you don't have to calculate that. And this is the rule for the derivative of a logarithm with any base. However, most of the logarithmic functions that you're going to be working with will be base e. So if we had base e, so if our base is e, which there's a special way of writing this, which I will write in a minute, but if our base is e, then when we look at our formula, we're going to have the log of e base e, and the log of e base e is simply 1. So that's equal to 1. The way we write log of u base e is like this, natural log of u. Therefore, if I was asked to find the derivative of natural log of u, which is log base e, it would be equal to 1 over u times that 1 that I mentioned, the log of e base e is 1, times du dx. So this is the formula we will be working with in all of these examples. We might have a logarithmic function of another base. I gave you the formula for that. I did an example. But when you look at applications in the real world, and probably in what you're doing, you're going to be working with natural logs predominantly. Before I get started with those examples, I just want to review some of the properties of logarithms because these properties are going to make it easier for us to differentiate. Remember, if you have the natural log or the log any base of a product, that's equal to the natural log of p plus the natural log of q. Similarly, if you have the natural log of a quotient, that will equal the natural log of p minus the natural log of q. If you have the natural log of q to the n, that's equal to n times the natural log of q. The reason that these properties are going to come in handy is they're going to allow us to get away from products, quotients, and powers, and then differentiate. So let's take a look at some examples. So in our first example, if we were asked to find the derivative of y equals natural log of x to the 5th, we can differentiate that. That will be 1 over u, so 1 over x to the 5th, times the derivative of x to the 5th, and the derivative of x to the 5th would be 5x to the 4th. When I simplify that, that will be equal to 5 over x. This was a fairly straightforward derivative, but I could have used my properties of logs and expressed that as y equals 5 times the natural log of x. That's the third property. which says if you have the logarithm of a quantity to an exponent, then you can express that as the exponent times the log of that quantity. So now we can take the derivative. The derivative of natural log of x is just 1 over x. So you can see that we get the same result using our property or doing it as is. Let's take a look at the next example. Here there's no properties I can use. I'm just going to differentiate this. 3 times the derivative of natural log of x squared minus 2 will be 1 over x squared minus 2, then multiplied by the derivative of x squared minus 2, which is 2x. So my final result will be 6x over x squared minus 2. In this next example, I'm going to show it using the property and not using the property, and you can decide what you prefer. So if we just differentiated this as is, the derivative would be 1 over x to the 4th plus 2x to the power of 3, so 1 over this u, and then we multiply by the du factor. So the du factor, I have to use my power rule, would be 3x to the 4th plus 2x to the power of n minus 1, which is 2. And then I go inside this and multiply by the derivative of x to the 4th plus 2x, which is 4x cubed plus 2. Now I can cancel an x to the 4th plus 2x squared, so my power will be 1, and I'm left with 12x cubed plus 6 in the numerator over x to the 4th plus 2x. So you don't need to use your properties. You can still differentiate. But I want to redo this question using my properties, and you'll see that it's a little bit easier. So I'm not going to find the derivative yet. I'm going to use my third property, which is I can bring this coefficient out front. Now I can differentiate. So the derivative will be 3 times, now I'm just dealing with this function, 1 over x to the 4th plus 2x, then multiply by the derivative of this, which is 4x cubed plus 2. When I simplify and distribute that 3, I will get 12x cubed plus 6 over x to the 4th plus 2x. So I get the same result, I just find it a little bit easier, but if you don't recognize to use your properties, you'll still get the same result. This next example looks very similar, but the power is on the log function. It's not on the quantity, therefore we have no properties to use. You have to think of this as being the natural log of x to the 4th plus 2x. This whole function is cubed. My property only works when only the quantity is raised to a power. So in this case, I do have to use my power rule. So the derivative will be 3 times this function to the power of 2, and now I go inside the power and multiply by the derivative of this function. So the derivative of natural log of this is 1 over x to the 4th plus 2x. And then I go inside the natural log function and multiply by the derivative of this polynomial. And that will be 4x cubed plus 2. So using your chain rule, we did our power, then our natural log, then our polynomial. And then when we clean this up a little bit, we will get, I'm going to distribute that 3 to here, 12x cubed plus 6. And then I'm going to write this as natural log squared, just a little cleaner way of expressing it, over x to the 4th plus 2x. So understand when the power is on the function, it's a different approach than when it's on the quantity. You can use the properties here, you can't there. The other thing I just want to point out, a lot of times I see students wanting to cancel because they see brackets, but this is not multiplication, it's the natural log of that. It's not natural log times that. So you cannot cancel an x to the 4th plus 2x. Okay, let's take a look at some more examples. In our next example, we have the natural log of a product. I can differentiate that the way it is. I would have to go 1 over this thing, and then when I multiply by the derivative of this, I would have to use the product rule. However, this is where I want to use my properties to make things much easier. When I have the natural log of something times something, I can express that as the natural log of the first factor plus the natural log of the second factor. And I'm just going to write that as x squared plus 1 to the power of 1/2. Now I could differentiate it like this, but because I have a power here, I can use my third property of logarithms that says this is equal to 1/2 natural log of x squared plus 1. So I use my first property to break up the product, and then I use my third property to move that exponent out of the exponent position. Now I'm going to differentiate. So my derivative will be 1 over 3x times the derivative of 3x plus 1/2 times the derivative of natural log of x squared plus 1 will be 1 over x squared plus 1, then times the derivative of x squared plus 1, which will be 2x. And that's all I have to do to differentiate it. I didn't need to use my product rule or my power rule. When I clean this up, I'm going to have 1 over x plus the 2's will cancel, and I'll have x over x squared plus 1. If you had done this question leaving it as a product, your answer would have been expressed as just one fraction. So this would be the equivalent if I were to get a common denominator and combine those two fractions. So I recommend that you use your properties to make it simpler whenever possible. Sometimes you won't have an option. For example, in this question here, this is a product. Very similar, but the change in the parentheses makes a totally different function. So this is a product, and in order to differentiate that, there's no properties I can use. I'm going to have to use my product rule. So I take natural log of 3x, multiply it to the derivative of this. This is to the 1/2. So the derivative would be 1/2 x squared plus 1 to the negative 1/2 times the derivative of x squared, which is 2x, plus x squared plus 1 to the 1/2 times the derivative of natural log of 3x, which would be 1 over 3x times 3. Then when I clean this up, the 1/2 and the 2 will cancel, and I'll have x times the natural log of 3x over x squared plus 1 to the 1/2. I moved it to the denominator so my exponent became positive, plus here the 3's cancel, and I will have x squared plus 1 to the 1/2 over x. If you need your answer expressed as one fraction, then you're going to need to get a common denominator and do the algebra to combine those. Let's take a look at a few more. In this question, I have the natural log of a quotient. Again, I would use my second property of logs to avoid using the quotient rule when I differentiate this thing. So I can express this as the natural log of 5x minus the natural log of 2x cubed plus 3. Then I differentiate. The derivative of natural log of 5x will be 1 over 5x times 5 minus the derivative of the natural log of that function will be 1 over 2x cubed plus 3 times the derivative of 2x cubed, which would be 6x squared. So my result would be 1 over x minus 6x squared over 2x cubed plus 3. In my last example, I have y equals the natural log of sine of 2x. So my derivative will be 1 over sine of 2x, and then my chain rule says I have to multiply by the derivative of this. The derivative of sine of 2x will be cos of 2x, and then I go inside the sine function and I multiply by the derivative of 2x, which is 2. When I clean this up, I'm going to get 2 cos of 2x over sine of 2x. You might think you're done, and I mean, this is correct, but probably if you were to look up the answer for a question like this, the author would simplify this using a trig identity. Cos of 2x over sine of 2x is cotangent of 2x. So you'd probably see the answer expressed like that. As usual, practice these rules in combination with all the other derivative formulas we've built up. And when you're ready, move on to the next video where we'll talk about derivatives of exponential functions. Take care and see you then.